Lesson 17, proportional situations. It just says here that situations that result in equivalent ratios. You would have done this last year, guys. It's just equivalent fractions, right? So my classic R, okay, in definition here, you're going to stick that word in there. So situations that result in equivalent ratios or rates are called proportional situations. Means they really mean exactly the same thing. So I'm going to use my classic fractions here. So if I have a 1-to-2 ratio or rate, and I want to compare it, and it's going to be equivalent to something, I'm going to compare it to 5-to-10 ratio. So those are perfectly the same fractions reduced, right? So if I can divide by 5, everything here in reduced would be actually equal to each other, right? It would be a half a fraction every single time. Now we spoke a little bit about this when we talked about it. Product of the means is equal to my crisscross method from lesson 13. A proportion is composed of 4 different terms, 4 pieces. Now we know the word terms from when we were doing the algebra and the equations. So this is what it means. So I'm going to put letters here so it's a little bit easier, okay? A, B, C, and D. So what this means is that these two across are my extremes. And these two across, different color here, B and C, are my means. So that's where they get the product of the extremes is equal to the product of the means. That's my crisscross method from lesson 13. The name extremes is given to the A and D terms, and the name means is given to the B and C terms. So we're really used to see this. Remember when we did the equations, when I said multiply this one and go across from lesson 13. Now this is a nice easy way to check also your work. Down here, so a nice easy, so if the numbers are nice and easy for you to verify, you want to compare 2 fractions, 2 ratios, 2 rates. So I'm going to use my really easy one here again. If you want to know if these were equal to each other, a nice easy method, like up top the page, is that I would take the product of these two. So I would multiply them. It gives me a nice easy 10. And if I multiply these two, it also gives me a 10. So therefore, 10 is equal to 10 coming from this expression. The product of the means across from each other is equal to the other product. So that's a nice, easy mental math way to check something. The problem is that it's not always easy numbers. You might have decimals or bigger numbers that obviously cannot do mental math. So you could just grab your calculator and do the same kind of check. In a table with values, the number from the first and the second column form a proportional series of numbers. So if I have a proportional situation, they tell you that it's a proportional table. So for example, if I have, I'm just going to call it my X and Y, we're used to that, right? So it might have different names to it. But let's say I have, 1, 4, 5, and 6. We can't really check mental math. Remember my consecutive numbers from lesson 4. And let's say I have this happening on the bottom. And they want to know what the proportionality coefficient is of this. They are telling you that it is a proportional table. So every single one of these fractions is really equal to each other. But they're asking you for proportionality coefficient. It's a little bit different. This is I call it my magic number. And there's one easy formula to do. It's y divided by x. So grab your bottom number, which is your y. Y divided by 6 is going to give you a 3. So your proportionality coefficient is a very simple one-step formula. Y divided by X. And if you do that for every single one of them, because it's proportional, they all have to give you a 3, 3, 3, and 3 all the way through, because they are all proportional table. Second page. Let's fill in the blanks here. The graph of a proportional situation is a oblique line. Oblique just means that it goes sideways a little bit like that, you know, that passes through the origin of the Cartesian plane, or on a line that passes through the origin of, yeah, just cross that out. That's just confusing for no reason. Okay. So what they're basically saying, graphs for proportional situations. The graph of proportional situation is a line, oblique, straight line that passes through. So that's two things. So hint, when I ask you guys what two things must happen in a proportional graph, it has to create a straight line that goes through, number 2, the origin. So for example, you have 2 examples of that down here. So that this here, right here, is your straight line that goes right through the origin. I often graph it just like this, guys, and I will say, you know, it obviously has to go through the center, 0, 0, the origin, but your line could also be down here, or it could be straight up, right? Depending on the situation, as long as it's a straight line. This one here has just the dots over here, but same idea. If you connect those dots, they would go right through, and I'm doing a terrible job with my straight line, is it would create that straight line going through the origin. Now, origin, it has to go through the 0, 0. So for example, these are no's, right? No, these are not proportional situations. So anything that does not start from the center, 0, 0, the origin. Anything, it could still be a straight line, but the second that, if it has a straight line, then it kind of tapers off and does something else, of course, not proportional. Anything with a curve to it, obviously nothing proportional. So really, it's just the classic, here, I'll try to use a line instead here. Okay, the classic straight line. And if I'm graphing that, right, so it has to go through the 0, 0, and it has to create a straight line. But any, right, so it could be straight up there, it could be way over here. It's as easy as that for what does a graph look like. And you're commenting and you're always saying straight line and always through the origin, the 0, 0. That's your justify in a question. So of course, if it has 0, 0, this kind of table, if it's X and Y, if 0 is being graphed, it has to go with a 0. And then after that, whatever the numbers may be, they obviously have to be the same numbers every time. So that's a 10, that's a 15, and that's a 20, because every single time you divide these, 10 divided by 2, 15 divided by 3, 20 divided, it always gives you a proportional coefficient, in this situation, of a 5. That creates a proportional table.